what to expect in experimental dosimetry. Until 1980s, the direct measurement of dose around the brachytherapy sources and applicators in support of clinical treatment planning and quality assurance was relatively uncommon, even within the research setting, let alone the clinical environment. Even today, the clinical quality assurance practice, like in our day-to-day clinic, is limited to experimental confirmation of strength and geometry of purchase source and applicator. And historically, this is due not only to this is not due to only difficulties of labor intensity of doing the measurements or difficulty of measurement, but also it's a consensus view that those measurements were so difficult and intrinsically inaccurate at small distances from seal sources that even a simplistic theoretical models were more reliable. So the dose measurement, but if you want to go for experimental brachytherapy, there were many challenges. The first of them would be the positional accuracy. The dose measurement requires a accurately positioned detectors. The positional accuracy is one of the major challenge in experimental dosimetry because of a very sharp dose gradient. As we all know, the data which we use, like mostly the TG43 data, what we are using is normalized at reference distance of 1 centimeter, which comes at the radial distances, which are very sensitive to this sharp dose gradients. If you talk about detector which can be used for this thing, the brachytherapy dose measurements plays a severe demands on detectors, since the dose distributions are characterized by large dose gradient, a large range of dose rates, and relatively low photon energies. The suitable detector must have a wide dynamic range, flat energy response, smaller size, high sensitivity. Nearly all detector systems explored to the date in brachytherapies are secondary detectors, the detectors that require calibration against radiation fields, usually low megavoltage photon beams, in which the dose rate is known as the detector, known at the detector location. So detector commonly used in this application include small TLDs or silicon diodes. And emerging technologies include radiochromic films, plastic scintillators, diamond detectors, and polymer gels. So if our need is to do a reference quality dose measurement in our experimental dosimetry, then there are few more demands on the detector, which are like there is uh, there is no hard and fast criteria for what constitutes a suitable dose measurement system for brachytherapy systems that provide credible reference quality measurement. There are generally a few characteristics which are desirable, like it should support absolute as well as relative measurement of dose at a geometric point in zero point 0.5 centimeter to 10 centimeter distance range in liquid water or solid water substitute media. Support a special density of a measurement of at least 5 mm or 5 degree in polar angles. Support dose measurement uncertainty is not greater than 10%, preferably not even more than 5% in that desirable radial ranges. And that uncertainty should include type A and type B kind of error. Support independent dose estimation should require minimal knowledge of should require minimal knowledge of dose distribution to correct for detector measurement artifacts. So if I would say practically, so no detector evaluate to date satisfy all these requirements. All currently used detectors, including organic detectors, radiochromic films, plastic scintillator, polymer gel, solid gel detectors such as diode, TLDs, are subjected to artifacts such as volume averaging, self attenuation, anisotropy, variable energy responses. So yes, we can always find a suitable detector for our needs, but first we need to specify what is our need, and then according to we can rule out some set of detectors which are useful for our purpose. So the second main concern is phantom size. Phantom size is also very important when you do experimental brachytherapy dosimetry, because there is something called boundary effect. Boundary effect in the dosage distribution is due to the variation of backscatter photons in the boundary region, have been widely reported in literature, and it do affect your measurements in a large scale. So in 2004, APM Task Group 43 report for the low energy photon emitting source reported that full scatter condition exists at a reference point r equals to 1 centimeter and theta 90 degree for all the studies, because the phantom size considered is large enough. Hence, the dose rate constant should be directly comparable in all cases. So we can say that two-dimensional anisotropy function is nearly independent of phantom size. However, it will definitely influence the radial dose function. because of the different scatter conditions. So yes, phantom shape and size is crucial parameters when we are doing the experimental brachytherapy dosimeters. So Genero et al. In 2008 done a study, and they concluded the equivalent phantom for a cylinder of 40 centimeter diameter and length 20 centimeter is a sphere of 20 centimeter in radius, and the equivalent phantom for the cube of 30 centimeter on each side is equivalent to sphere of 15.5 centimeter in radius. This method has been validated upon comparing 20 published datasets with validating typically within 2%. So yes, this conclusion can be used for your experimental design because it was validated by a lot of published data. So let's move to the other parameter, that is phantom material. Yes, it is not that important like a phantom size and range, but yes, it is important. So phantom axis, like for several solid phantom materials have been tested regarding like water substitute for dosimetric measurements in brachytherapy. Phantom axis up to 10 centimeter was considered as clinically relevant. Why clinically relevant? Because whatever dose you have at radial distances 1 centimeter normalized at that point of radial distances approximately became 1/10 of its value at nearly 10 centimeters in brachytherapy settings. That's why in most of the studies or in experiment, this radial distances up to the 10 centimeters were considered clinically relevant. The tested phantom materials showed significant differences in degree of water equivalence. So in phantom with radii up to 10 centimeters, this for the first category of phantoms were have percentage deviation from water phantom, which is less than 0.8%. And the other category of phantom, which include original plastic water, blue water, polythene, polystyrene, they comes in category less than 2%, 2.6% variation from water. So let's move to the other category, like for the large sizes. Just a moment. Okay. So for the larger phantom radii up to 30 centimeters. So the first category of phantom shows a variation of approx 1.4%, and the other category of phantom shows a large variation up to 8.1%. And if we move to the a category like polymethyl methacrylate, that is PMMA, it plays a separate role with deviation up to 4.3% for radii not exceeding 10 centimeters, but approximately 1% for radii up to 30 centimeters. So definitely PMMA can be a definite choice if you are going for a large dimension setting or experimental setting for the phantom. These results are well compared in the literature. These are some studies which have concluded the same kind of findings. Even the paper from the Andrew Schoenfield has validated it with the peer review. But that kind of reference you can find in the reference section, which I have given later in the presentation. So although phantom dimension is the most important single factor influencing the dose distribution around HDR sources, the effect of material property is non-negotiable because becomes increasingly important as phantom dimension increases. The importance of knowing the size of the water phantom dose data underlies treatment planning system when using such data as a reference. Example, if you are doing a detector evolution study, it is very important to achieve the highest possible accuracy in experimental dosimetry, or the phantom specific correction factors should be used. If they are used, it is always better for accuracy, and it will definitely affect your results. So these are the findings which we have observed in the literature or with the basic group studies, group experimental data. So let me summarize this. What are the possible solution if we have to start experimental setup and we are clear in our mind like what we basically wants to do? Then the possible solutions could be. So if you are intended to use it for you want to make a setup for a reference dosimetry in brachytherapy. So these are the preferred choice of detectors. So definitely ionization chambers can yield a measurement of nearly absolute dose, but definitely it required a lot of correction factors. Semiconductor detectors can be of good choice. They have a high spatial resolution, smaller size, good response, but definitely it has a sensitivity to energy depend. It has a large energy dependence, And of course, it is not comparable to tissue. Radiochromic films are the excellent choice. They have high spatial resolution. They are very cost effective. They have water equivalence. But yes, it is little cumbersome, and scanners and that kind of characterizing film and obtaining dosimetric results are kind of a process which we have to get through. We have to characterize our film every time. And TLDs also have been proved to be an excellent choice for experimental brachytherapy in the reference setup, because they are small and accessible in variety of formats. Like you can get them in powder, you can get them in dots, you can get them in cylindrical shape. They have high accuracy. If we have to, like, we have to characterize them, and we have to do a laborious, annealing assessment kind of process. But yes, they can fetch you high accuracy if done in a proper manner. They are very cost effective, and of course they can be reused. So a TLD can be a good choice. And diamond detector can yield a measurement of nearly absolute dose. In our own experimental setup, we have found it to be an excellent choice to do a reference dosimetry in experimental brachytherapy. But yes, there is a small disadvantage that it is costly. But if you have this with your institution, then it is a perfect choice. So, for the reference dosimetry, if we talk about what is the preferred choice of phantom, so I would say a radiation field analyzer can be employed for such kind of a dosimetry. But the other choice of phantom could be this one, like original plastic water, R1, RW1, RW3, solid water, He solid water, virtual water, plastic water DT, plastic water LR phantoms, original plastic water, and PMMA. So, if we want to have experimental setup, brachytherapy dosimetry setup for verification, validation, and quality assurance of treatment planning system, so the preferred choice of detector could be this. So, I would say the radiochromic films are the first detector of choice and always preferred, because it has a high spatial resolution, which is mostly desirable when you do verification and validation. And they are very cost effective, water equivalent, and of course scanners are required for characterizing film, and it is a little bit cumbersome. But yes, radiochromic films have proved to be a very reliable detector in experimental dosimetry method. Later in the presentation, I will share you some robust experimental studies and models which employed radiochromic films for this verification and validation and quality assurance purpose in experimental brachytherapy. TLD could be a good choice because it's small, accessible in variety of formats, high accuracy, cost effective. Other choice could be OSLE. So they are little less in a laborious process in comparison to TLD. However, it has a lot of advantage what TLDs have. Nowadays, people are using even ionization array, like which comes with the matrix or octavius detectors, which comes with the liquid filled ionization chambers, or even air filled ionization chamber. They have a ease of use. They have high spatial resolution, and of course, it can be reused. They are costly, but if your organization or institute have it, it will definitely can play a key role in your experimental setup. So the other detectors can be your plastic scintillation detector, your inorganic scintillation detector, your fat panel detector, MOSFET, because some few of the studies have reported these detectors and they have shown a satisfactory results. But I would say that radiochromic films are the could be the preferred choices, and they always give very reproducible results. So, but in the recent developments, gel dosimetry is also expanding in experimental brachytherapy dosimetry, with reported ease of use and reproducible results. These are some studies which have employed the gel dosimetry and showed a very robust and reproducible design. So for this kind of experimental dosimetry, preferred choice of phantom could be this one. But even you can use original plastic water, blue water, polystyrene, phantoms for because it's a relative dosimetry, and you are definitely analyzing it with some TPS thing. So it's relative kind of a dosimetry. So definitely, if you have any of the below mentioned phantom, then we can definitely go with them as well. So these are the things which we have. These are the crux of the literature what we have on experimental dosimetry till now. So for an example, like how we can start the experimental dosimetry, let me share our design of experiment which we have used, for our reference experimental dosimetry in brachytherapy. If you wish, you can use this reference design as it is, or you can do your modulation with your needs. So what we have done is we have done experimental validation of TG43 brachytherapy dose evaluation formalism for high dose rate cobalt 60 brachytherapy source, and the findings were presented and published in IRPA 15 Congress. And the group was considered by with Professor Chogle, Professor Zakaria, Professor Autosor, Professor Frank Hansley, Dr. Sonja Webinar, myself, and Dr. Patrick Kessler. So this work has been planned to analyze the challenge and a design of a method of experimental dosimetry. Experimental experiment measurements are designed to investigate the radial dose function for cobalt 60 HDR brachytherapy source. So for this present work, we have chosen two reference point, that is 1 centimeter, that is there always, and 4 centimeter. The 4 centimeter as a reference point we have chosen just to analyze the data effectively and rule out the uncertainty due to positional accuracy. The present work also explored the applicability of various detectors for the experimental HDR brachytherapy dosimetry, and the role of effective point of measurement and volume averaging were also analyzed in this study. So all the experiments were conducted in MP3M water phantom. All measurements were performed in distilled water. A heavy density rectangular rod were used across the phantom with the in-house 3D printed needle holder, and applicator was simple geometry of straight steel needle. A Bibic Segenova Eckhart Ziegler machine was used for the experiments. This is a typical experimental setup. So now you can see there is a needle, and you can see a diode, and this is the guide tube, and this is the phantom which we have employed for the work. So MP3M, Mephisto, MC Square software, and the original Pro software was used for localization of center of the source. So basically, this whole study is divided into two categories. The first category, in the first part, I'm sorry, it is divided in two parts. The first part considered like doing an exercise to find the center of the source, because it is very important to measure the radial dose distribution. That because you have to be at the center of the source exactly, and it is very sensitive to positional accuracy. So yes, this process is very important while doing the measurement. And the other part of study, once you have find out the center of the source, then the other part of the study considered the measurement of radial dose function. So for finding the center of the source, first we have manually positioned the detector so that its symmetry axis parallel to the needle's symmetry axis underneath the needle, roughly in the center of needle tip. Second, the detector takes the PDD profile along the longitudinal axis of the source. And third, inline and cross-line profiles was acquired underneath the source. This is the pictorial representation of experimental design. So this was the source in the needle. So we have taken a PDD profile in this direction and inline and cross-line profiles underneath the needles. And that is how we have found the center of the source with exact coordinates X and Y and Z. So next, after localization scans, the origin of measurements were identified. That is the center of the detector. So after this, we have employed the detector to acquire the radial profiles. So in this present work, we have included 5 detectors just to see their workability in this particular experimental settings. So 3 of them were ionization chambers, 2 of them were semiflex chambers, and one is pinpoint chamber. Other was micro diamond, and the last one was diode. So the two different orientation of detectors were used to deal with the volume averaging effect in ionization chambers and to have maximum efficiency in solid state detectors. So these are the typical kind of orientation which we have used. This kind of orientation for ionization chamber, because this provide you edge over the volume averaging effects, and definitely this kind of orientation for solid state detectors, basically macro diamond and diode, just to increase their efficiency. So radial dose profiles acquisition were planned to direct in an outward direction ranging over radial distance from 6 mm to 150 mm. Depending on the type of a detector, either 5 or 15 seconds were chosen for the electrometer integration time per point of measurement. For every detector, three consecutive measurements of radial dose profiles were analyzed for standard deviation and reproducibility. So what we have found with the experiment is like for every measurement, fluctuation was observed with the source center. The acquired and but however the acquired data were quite reproducible. The profiles were found reproducible within 0.5% of each other for the whole range of measurement for both of the semi-flex chambers and the diode. The pinpoint ionization chamber was found reproducible within 0.6% up to 80 mm of radial distance, and after this the reproducibility was 2.3% of other consecutive measurements. For the micro diamond detector, the measurements were found reproducible within 0.5% up to 12 centimeters of radial distance, and after this reproducibility was around 1.17% for the consecutive measurements. The iterative method of analysis were employed to find the effective point of measurement for different detectors with reference to TG43 data. And we have found the E2M correction within the range of minus zero point 0.2 mm to 0.5 mm for all the three ionization chamber. And this range or this magnitude of correction factor cannot be considered as an effective point of measurement for the detector, as it's very small in magnitude. So therefore, this correction can be considered as an error in detector placement or positioning. So the present work recommends the use of same orientation for ionization chamber to avoid the significant effective point of measurement corrections in HDR brachytherapy experimental dosimetry design. Present work also evaluated volume averaging effect for ionization chamber with different volumes, and the volume averaging correction for the ionization chamber of such small volumes were sufficiently close to unity at large radial distances, which is greater than 3 centimeters. So the radial dose functions were calculated according to the APM TG43 report for every detector. And the radial and the acquired radial functions were analyzed for two chosen reference point, like I have mentioned earlier, that is radial distance 1 centimeter and 4 centimeter, and it is compared to the reference APM TG consist data, which is obtained with the Monte Carlo simulation studies. So this is the graphical illustration of experimentally acquired radial function for all the 5 detectors compared to AAPM1. So the yellow one you can see is the TG43 Monte Carlo data, and these were all other detectors. So now you can see the PW31013, the semiflex chamber, the other semiflex chamber 31010, and the diamond detector has shown a good parallel results. It can be more clear if we have also normalized this for 4 centimeter, and now we can see the behavior in a smooth manner. So it is clear now. We can clearly observe like diamond detector. The both of the semiflex detectors are quite promising when you are doing experimental reference dosimetry. However, the diode and the pinpoint chamber were not found very suitable. They overrespond for the later radial functions, and they behave ambiguous for the small radial functions, means less than like 3 or 4 centimeters. So what are the results which we get? So we got the useful radial ranges for the different detectors. So for micro diamond, the useful range is 1 to 10 centimeters, and the percentage of variation within useful radial range is 3.2%. The semi-flex one are the small volume one is very useful from 2 to 14 centimeters, and semi-flex for semi-flex large volume like 0.3 cc one was very good for 4 and 14 centimeter with the percentage variation of within 1.9%. So PTW pinpoint chambers and diode were over responding at large distances, and this could be because diode are very energy dependent. For the pinpoint ionization chamber, the anode inside were made up of steel as a material. So we have concluded that it is because of that particular material. So this work has demonstrated the detector with a small volume and low energy dependence are detector of choice for experimental dosimetry in HDR brachytherapy. It was observed that the small individual characteristic of detector were more important instead of basic type of a detector. It means we can't say the solid state detectors are superior or the ionization chambers are superior. You can always find a suitable detector in different categories of detector. Like we have found a diamond detector in solid state category, two semi-flex small volume chambers quite suitable for dosimetry in ionization chamber type of detectors. So both the categories of detectors, solid state and ionization chamber, have several suitable detector options for HDR brachytherapy dosimetry, especially for cobalt 60. The present work has provided a reference design. Like if you can observe in this study, we have used almost all the equipment which are already present in a normal radiotherapy clinic. That is your RFA, the detectors available with the department, your Mephisto software, which is generally employed with the RFA when you use the EBRT measurements. So yes, it is quite doable, and there are many examples of the study which they in where they have shown a very robust design and reproducible results. In this study, we concluded that micro diamond and small volume semiflex ionization chambers were found suitable for experimental dosimetry for the clinically relevant radial distances. So now I'm mentioning some of the studies which can be, if you are interested, you can go through them. They are very good in, like what I mean is they have a very robust design and very reproducible kind of a setting or the measurements and results. So these are some example. If you are interested in reference dosimetry in experimental brachytherapy stream. If you are interested in something like for quality assurance and verification and dosimetry, these are some of the examples of some of the study with a robust design. These are the references for my whole talk. And thank you very much. If you have any question, I'm happy to answer.
Uh, Thank you, Dr. Rajni, for such a wonderful presentations. I must say, I think, of course, you have reviewed all the literatures relevant to this topic, and you also have highlighted all the characteristic requirement for a dosimetry in terms of detectors, in terms of phantoms, and in terms of experimental setup. And of course, I think your experimental validation was quite interesting. And at the moment, I don't see any questions in the chat box. And if any attendees would like to ask any questions to Dr. Rajni, please do so. Okay, so if there is no questions from the attendee, let me just try to understand something from you. So, of course, your validation was purely based on TG43.
Yes.
About the new TG, TG186, wherein the heterogeneity was taken into consideration. So
For the
can your method be extended to do the validations for the TG186? And if so, what kind of modifications you need to do in your experimental setup?
Uh, Thank you very much, sir, for the question. However, our studies were till now, our study were limited to experimental validation of TG43. We have not yet planned for that because still we are in process of validating some other detectors. But definitely, I have to work on this because I'm not sure what kind of corrections which or maybe we have to change the whole a kind of a measurement technique when we are going for that report, but yes, it's a good suggestion, but I'm not sure now like what could be the corrections because we are in process, still we are in the same experiment, but definitely we will definitely go through it and we will see if we can extend our same design for that validation.
And one question is, and what could be the reason why the diet and the chamber, pinpoint chamber was not responding as expected? Is it something to do with the orientation of the
Like with our
detector?
observation, sir, that pinpoint chamber were having a node with steel as a material. So we have seen that kind of a spike in the measurement when the anode material is usually steel.
Yeah.
So for the pinpoint chamber, we have concluded that ambiguous behavior at the larger distances were because of that material. And for the diodes, as we all know, diodes has very high energy dependence. Most of
Yeah.
the time, they
Beyond
over
that, I
respond
think
for the
above, yeah, above that, I think what I'm wondering is it because of the shielded or unshielded natures of the diode, and that is something to do with the orientation of the diodes again? Right now, I think I'm not very sure. I'm not able to recollect whether the PTW diode is a shielded or unshielded. If you can throw some
shielded one.
light onto
It
that,
was shielded one.
it's a shielded one. So in that case, suppose if you change the orientations of the detector, will the response be improved and be comparable or near to the Monte Carlo calculated response?
Um, yes, that could be one reason. We have not explored, like we do not have that unshielded one, so we have not practically performed a study with that. But yes, that could be one reason. For now, what we have done, we have attributed that kind of a behavior because of its energy dependence. But definitely, as you have raised a question, it could be because of its shielded and unshielded design, and it can give you good, it can give us insight. If we will definitely try to incorporate and see if it is due to that, but for now I'm not sure if it's due to that,
See,
because
there
we
is
have
a
attributed from the other characteristic study of the same detector, and for the other experimental dosimetry also, they have over responded a bit uh, in the scattering medium. Means once you are at the larger radial distances, they mostly over respond, and they have concluded it's because of their high energy dependence. So for now, yes, we are attributing it to because of their energy dependence only. But yes, that could be that shielding and unshielding could be a reason, or maybe something, maybe a reason, maybe a factor which can incorporate in this.
Mhm. I think so. We have a questions from Nigar Sharmin. I think her question is, can we have the presentation? And of course, I think we have already shared presentations in one of the Google Drive.
Uh, yes, we can do that, but unfortunately today we were not, due to some technical issues, we were not able to record the video. Otherwise,
Okay.
a form webinars are mostly available in YouTube videos, even afterwards also. But definitely, we will definitely can put this on website for some time, or maybe in a Google Drive, and share the link with you all if presentation is requested.
Uh, okay, there is one more. There is one more question. Which detector has most closest result with that of TPS?
Sorry.
Which detector has most closest results with that of TPS?
I would say radiochromic films. If you have to validate the TPS, treatment planning system, or you have to do the quality assurance. So, in my opinion, what I have observed and what the literature has shown is radiochromic films can be a detector of a choice, no doubt, and they have shown a very promising results with
So that
great
question, yeah, that
reproducibility
question
and
is
ease of use also, because it has a, because spatial resolution is something which is very important when you are doing validation in TPS planning. So radiochromic films are definitely provide a very good spatial resolution, and that kind of insight into the verification.
But at the same time, you did also mention that the volume averaging effect for most of the detectors are unit or
Yes.
one. So in that case, I think is the resolution of the detector is the only parameters why you would prefer for the radiochromic film, or there is something else also.
No, because yeah, thanks for the come in, sir. But why I concluded that radiochromic is a preferred choice of thing, because when we are doing this volume averaging, effect correction, and everything are very important when you are doing an absolute or reference dosimetry. But when you are doing a TPS study, when you are doing a verification, which is otherwise relative, because in treatment planning system itself you are doing a lot of assumptions and you are validating it. So I think for that kind of requirement, radiochromic film can work wonders, and literature has shown a good results, and quite they are quite reproducible also with dosimetry, and of course very cost effective also.
So we got one more questions from Srishti, and the questions is, are there any specific different correction factor to be used for different dosimeters for this study?
Thanks for the question. I would say, again, it depends on your needs, like what you have planned to do. If you are doing a reference study, then definitely most of the correction factors, if you're using ionization chamber, the correction factor related to ionization chambers and other things like phantom size correction factors, phantom material correction factors, all those things needs to be incorporated if you want to be in a uncertainty, which is which makes sense in the measurement. But if you're doing a relative measurement, yes, you can always neglect some of the minor corrections for the dosimeters. uh, like small corrections can be omitted in relative dosimetry, so it depends basically on your needs, like what you're planning to do. So for relative dosimetry, yes, you can ease out on that.
At the moment, okay, there is one more questions from Rina P.S. Have you studied the angular dependence for diode detectors?
For our experimental design, we haven't, because we have only measured radial dose distributions. We have not done any kind of, polar measurements or two-dimensional anisotropic measurements. Uh, so yes, we haven't done for our work.
Okay, that seems to be the only questions available in the chat box. If there is any other questions for Dr. Rajni, please do put your questions on the chat box so that she can answer. Okay, if not, I think I would like to thank uh, uh, the Rajni for such elaborative presentations and explaining and sharing their experiences on developing a reference dosimetry for brachytherapy shots, especially for cobalt 60. And at the same time, I think I would like to thank the educational committee chair for giving me this opportunity to conduct this webinar. And at the end, I think I would like to thank all the participants and for making this webinar successful. So I would like to hand over the session
Thank you very much,
to
sir,
the
for
chair.
moderating the presentation, and have a wonderful opportunity to discuss these things with you all. So thank you, participants. Thank you, Dayananda sir, and of course the AFOMP platform for giving such platform. Thank you so much. So can we have Professor Jin? Professor Jin, are you there? Okay, if he's not there, so I take a liberty to thank Professor Dayanand to being with us today. And I have news for all of you. Like AFOM Awards has been already published, means they were open for the application, and now the date is extended up to 12th of May. So please feel free and apply for the awards. And thank you very much for being with us for the whole presentation and making this session a success. So thank you so much for being with us.
Okay, see you in the next webinar.
Yes, definitely.